Hello students, welcome to this lecture on interconnects. So this is an introduction to the interconnects, or also called as wiring in the CMOS VLSI design. Generally what happens is whenever we are having a lot of transistors, the transistors are anyways connected by the wires to the other transistors. So those set of these are one type of interconnects. The other type of interconnects are the wirings which connect from one subsystem to the another subsystem. So in that sense, if one is actually designing a subsystem, and then in one part of the chip, and then there is another subsystem which is there on the other part of the chip, and so there will be and both the systems has to be connected. So then a wire, an electrical wiring has to be done from one end to the other end, and that too on the chip. So that forms another type of interconnects. So there are actually several types of interconnects, the global level interconnects or the local interconnects and so on. And that's where the interconnects the interconnects designing plays a very crucial role in the overall system design in the chip. What we are going to learn in this particular lecture series about interconnects is how the interconnects or the wiring is going to affect the overall performance of the design, right? So if I have, in a very simple form, if I have an inverter connected to another inverter, and if I see a kind of a long wire there, what is bound to happen? Whether the inverter connected to an inverter without the interconnects, how does it perform, and then with the interconnects, how does it perform? All right, so the basic characteristics of the interconnects is in the form of a resistance or a capacitance. So generally, whenever a wire element or a interconnect component is available in our design, we try to characterize it in terms of the resistance and then the capacitance. And once we have the resistance and then the capacitance, we can actually easily integrate with that of our transistor resistance and capacitance model. And then we can use any kind of the Elmore delay method to estimate the overall delay, or to estimate any other parameters. So generally, you will see that the interconnects are kind of characterized in terms of the resistance and then the capacitance. Now, how do we evaluate a resistance and the capacitance given an interconnect? The resistance part of it is quite simple. It's kind of very elementary. So if you look into this particular wire, uh, with the wire A and B, and I've shown here as a block of wire with a width of W and then the length of L for this particular wire, and then there is a thickness T. So as per our Ohm's law, or the definition, the resistance is nothing but, of course, the voltage by the current. But in terms of the the material or the dimension level definition of the resistance, it turns out to be rho L by A, where rho is the resistivity of the material that has been used, and L is the length dimensions, and then area is nothing but the width multiplied by the thickness. Um, and so this can also be rewritten in the form of rho by T, so resistivity by thickness, and then multiplied by L by W. Turns out that this particular definition of resistance, we can also express it in the form of the sheet resistance. So this is the sheet resistance multiplied by L by W. Now this sheet resistance has a very important property. That the reason is this thickness. So let me pick up a pointer. So the thickness here is actually a technology or a process parameter. We cannot change with respect to the design. So it is a process dependent. And rho is a material dependent. Again, we can call it to be a process kind of a dependent. So for example, 65 nanometer technology or 180 nanometer technology uses the copper as the wiring material or the interconnect material. So this remains fixed for a process parameters, and then T remains fixed. The thickness is usually comes from the deposition process, and for all the interconnects at different levels, we will define the thickness, right? So in that sense, the thickness is kind of defined for every layer or for every level in a particular process technology node. So if I pick one level of the interconnects, then its thickness is defined, or it is, you can consider it to be constant. So in that sense, we can redefine this rho by T as a sheet resistance. And if we know this sheet resistance for a particular process node with different levels, then we can easily calculate the resistance of the interconnect at different levels based on its design parameters L and W. Right? The sheet resistance, the units of the sheet resistance is pretty simple. It is nothing but, this is the resistance. The unit is ohms. So the sheet resistance will have actually ohms and ohms per square. All right. The copper has a resistivity of 2.2, and the aluminum has a resistivity of 2.8 micro ohm centimeter. Right? Aluminum is generally kind of outdated, and it is mostly copper, which has been used in the recent semiconductor industry, or in the regular process parameters. So we will see mostly the copper as the wiring material in most of the process technology nodes, and aluminum will not be used. But I've given both the aluminum and copper just to just to look at these values of 2.2 and 2.8, which implies that the copper has a better conductivity properties. In the sense that the resistivity is low for the copper when compared with that of the aluminum, and in that sense, the conductivity of the copper is better. And what it really helps is, if the conductivity is better, the current, the current will be better, and thereby it improves the performance. The other advantage of having the copper is, there's a standardized copper reverse electroplating method, and that has become more standardized. That has been very well characterized or very well calibrated, and in that sense, the copper for the deposition, the copper deposition process has become really a well-known or an accepted method, and that is one of the reasons why the copper has been showing good results, and it is widely accepted. Moving ahead, so this is what we have for a dimensions of W and L of the copper wire. We have the sheet resistance multiplied by L by W, right? Now tomorrow, if I change this dimensions to 2L and then 2W, so this is what I have shown here, 2L and 2W, the resistance, right, of 2W and 2L, assuming that both of them are the same material of copper, and assuming it is the same level in the process, in the technology node process, then the thickness will also be the same. Only thing that will change is W and L, and if it increases twice that of the first block of wire, still the resistance remains the same, because the L and W, which is taken as a ratio here, it will be scaled by 2 times, but 2 and 2 will get cancelled, and then finally we will have a resistance equal to that of W comma L. So resistance of 2W comma 2L will be similar to that of the resistance of W comma L. So the resistance of the wire is actually independent of equal scaling of the width and the length, right? So what it really implies is, if I have L and W, and if I equally scale it, both the length and the width, to 2 times or to the n times, I will once again get the same resistance. All right. Now, if suppose I have a resistance of say RW comma 2L, and tomorrow I will increase it to say 2W comma 4L, then also both this resistance are equal, right? So equal scaling on the length and length and width will give me the same resistance, right? Hope this is clear. Moving ahead, so just an example, just to find out what should be the resistance of the copper wire. Generally, we will see in the VLSI design. So the thickness parameters for a 65 nanometer technology node for one of the medium levels will be 0.22 micron. That will be the thickness. The width for this particular design is 0.125 micron. And suppose if I have a long wire of 1 millimeter, what should be the resistance? And I also wanted to evaluate what should be the sheet resistance. The sheet resistance is pretty simple based on the the resistivity of the copper, and then divided by the thickness, which is 0.125 micron, or rather the thickness is 0.22 micron. So this is 0.22 micron, and then this is 2.2 micro ohm centimeter for the copper. So this is basically 2.2 to 10 raised to minus 6, and this is centimeter. So this in the denominator side, I can actually make it into centimeter, 0.22 into 10 raised to minus 4 centimeter. So if I have centimeter and centimeter, it will get cancelled, and finally we will get 2.2 into 10 raised to minus 6, and then divided by 0.22. So 10 raised to minus 5 and divided by 10 raised to minus 4. So it will eventually give me 0.1 ohms ohm per square. So that is the units of the sheet resistance. The resistance of this particular wire, so I've written the copper wire here, is nothing but rho L by area. So rho is 2.2 micro ohm centimeter multiplied by 1 mm long wire. So it will be nothing but 10 raised to minus 1 centimeter, converting everything to the centimeters. And the thickness and then the width is 0.22 into 10 raised to minus 4, and then the width is 0.125 into 10 raised to minus 4. We will get around 800 ohms. Right, again, hope this example is clear. So what it means is, with this particular the dimensions which we will normally see in the digital VLSI design on a chip, the resistance is around 800 ohms, and this will have an impact on the overall performance of the design. As I said earlier, the interconnects will always be characterized with a resistance and then a capacitance. So how do you evaluate the capacitance? So one of the very simple method to estimate the capacitance of the wire is using the parallel plate capacitor model. So what it means is, if I have a interconnect or a wire component here with the dimensions of W, L, and then the distance between the another metal wire, it could be running horizontally or it could be running laterally. So in that sense, if the distance between or the spacing between them is h here, then I can easily calculate what is the capacitance here, because we can assume this to be one metal plate. The another one, although I've written as a ground plane, it could be any other metal layers beneath it or above this particular interconnect or the wiring component, right? So anything above this and then below this will form kind of a parallel plate capacitor. So because we have two metal plates, one here, one of this one, and then the another one beneath this, or it could be above this also. So that forms the second metal plate, and between that we have the dielectric. It is always isolated by the dielectric silicon dioxide. So we get this capacitor there between the two plates, and in between and then sandwiching the dielectric material. So in that sense, the parallel plate capacitance value is nothing but epsilon naught of oxide, because oxide is the dielectric which we are going to use. Of course, there should be epsilon naught and then epsilon naught oxide. Epsilon naught oxide, epsilon naught oxide is nothing but epsilon naught into K of oxide, where K of oxide is the dielectric constant of silicon dioxide is 3.9. Of course, epsilon value will be nothing but 8.854 into 10 raised to minus 14 farad per centimeter. And then we have the W and L divided by H. So W and L parameter, if it is known and then the spacing H is known, then we should be able to find out what is the capacitance that this particular interconnect is characterized. Now remember that the parallel plate capacitance is this is directly proportional to the L. Resistance of the wire is also directly proportional to the L. So in that sense, both of them is directly proportional to the length of the wire. So if I keep increasing this length of the wire, both the capacitance and then the resistance of the wire is likely to increase, and it will have a drastic effect on the overall system performance. Right. The other parameter to be interesting to note is the W parameter. So if I have the wire, the resistance of the wire is inversely proportional to the W. The capacitance of the wire, if I consider this parallel plate capacitance, the capacitance of the wire is directly proportional to the W. So an increase in the W here is likely to decrease the resistance of the wire. An increase in the W here is likely to increase the capacitance of the wire. Turns out to be a very, very similar relationship when we calculated or when we try to model the transistors with the width, right? So when we try to scale the width of the transistors, its resistance used to decrease, but its parasitic capacitance used to increase, right? So in the similar sense, we will have this particular parameter, and somewhere this will be this will form a major component in optimizing the design width of the wire. All right, similar to how we had seen the transistor width and how an optimized width is required for the transistor so that we get the minimum delay. Similarly, the same ideology will be used to identify the optimized width of the wire so that we'll get the minimum performance, or the minimum delay for the overall circuits, which consist of the interconnects. So hope this is clear. So let's look into the modeling the delay for an interconnect. Let's say that the interconnect is 1 mm long. So 1 mm long interconnect, or one can also argue that it could be a very long wire. So as such, if I have a very long wire, it will have, we can always have it as a distributed component, right? So, and then use that particular distributed component to model our interconnects resistance and then the capacitance, and then use that or integrate that into our circuit for estimating the overall performance, delay, power, and other aspects, right? So what we are trying to see here is interconnect is a distributed circuit, right? It's a distributed circuit in the sense, if I have a long interconnect, right, A to B, we say that if I can actually distribute it among different segments, each of the segments will have a resistance, it will have a capacitance. Each of the segments will have a resistance, capacitance, and each of the segments will have a resistance and capacitance. So that's what the distributed circuit says, where R and C are modeled as the lumped elements. Right, lumped elements in the sense the passive elements are resistance and then the capacitance. So if you do this particular distributed model of an interconnect, it actually becomes very simple. It simplifies our overall estimation of the delay and power and other statistics, right? But while we are actually distributing the circuit, right, so each of these segments could be modeled as an L model, it could be modeled as a pi model, and it could be modeled as the T model. And the naming of this particular model is actually is the way the R and C are positioned, right? So the L model will have the R and C like this. The pi model will have C by 2 component, C by 2 component, and then in between that there will be a resistance R. The T model, we have R by 2 and R by 2, and then there will be a capacitance in between that, right? Notice that in all the three models, we are considering single segment or a single distributed part of the interconnect, where the single segment is having an overall resistance of R and then a capacitance of C, right? And similarly in the pi model, the overall, the segment should have a resistance of R, capacitance of C. So that's why being a pi model, it's actually showing C by 2 here on one side and C by 2 on the other side. And then similarly T model, one segment, each segment has a total resistance of R and then the capacitance of C. So in the T model, what it does is R by 2, it separates it out on one side and the other side, and in between there is a C. And if I want to find out the overall delay here for this particular L model circuit, it turns out to be R multiplied by C. Right, so for this one, if this is the input signal and then this is the output, I will get R into C by 2 as the delay. And for the T model, if this is the input and then this is of course this will be the output, because R by 2, this is left floating. So even if this one and then if I take this one, both the outputs will be similar. There won't be any current that will be flowing here, and that's why whatever is the voltage that has been accumulated here will be the same as here. So in that sense, the delay will be nothing but R by 2 and multiplied by C. So it will be RC by 2. So notice that for the L model, I will get an delay of RC. For pi model, it is the RC by 2. And then for the T model, it is RC by 2. Right? So let's go to the 3 segments. So I have an interconnect. I have a wire here basically. Its resistance is R and its capacitance is C. And now we have actually distributed into 3 components. So the 3 parts, so this is one part, one segment, this is second segment, this is the third segment, right? So what we are saying is it has been distributed. So the overall resistance is actually distributed to R by 3, C by 3. This one is also distributed to R by 3, C by 3. And then this one is also distributed to R by 3, C by 3. So overall, I will have a resistance of R and a capacitance of C by 3. So if I consider this particular model or this particular segment, so that will be this particular segment in the L model, right? So if I consider this particular segment, the first of the 3 segments, and then actually use the L model for the first segment, I'll get R and C. So it is basically R by 3 and C by 3. Second segment is, this one, R by 3 and C by 3. Then the third segment is R by 3, C by 3. The overall delay for the 3 segments will be nothing but starting from here and then here. So it will be, using the Elmore delay method, I should be able to find out what is the overall delay. So this is R by 3 multiplied by C by 3. This is 2R by 3 multiplied by C by 3. And this is 3R by 3 multiplied by C by 3. Overall, I'll get 2 by 3 RC. If I use the single segment in the form of a pi model, then I will get C by 3 and R by 3. So I will have C by 3's 2 parts. I will do 2 parts of C by 3. I'll get C by 6 on this side, C by 6 on this side, and in between I will have R by 3. So this will represent the first segment. The second segment will be the similar, C by 6 on either side of R by 3. And then the third segment will be C by 6, and then R by 3 in between that. Right, so overall, I'll get a delay of again RC by 2 here. Right, so if I do R by 3 into C by 6 and C by 6 in parallel, will give me C by 3 here. So overall RC by 9 plus 2R by 3 multiplied by C by 3. So 2RC by 9. And then overall this R multiplied by C by 6 will give me 3RC by 18. Finally, the delay is RC by 2. For the T model, again, individual segments is having a resistance of R by 3 and C by 3. So here in the T model, the resistance is actually divided into 2 parts. On one part, it is kept on one side of the C by 3. The other side, it is the remaining resistance. So it becomes R by 6 and R by 6, and in between there is a C by 3. This will be one segment. Similarly, second segment will be this one. Third segment will be this one. And the overall delay will be nothing but RC by 18, this R by 6 multiplied by C by 3. And this R by 6, this R by 6, and this R by 6 multiplied by C by 3. And then finally, I will have 1, 2, 3, 4, 5 R by 6 multiplied by C by 3. So finally, I'll get a delay of RC by 2. Right? Notice that in the previous slide, when we had only one segment, this particular interconnect was actually seen as one segment. We got a delay of RC in the L model. We got a delay of RC by 2. We got a delay of RC by 2 in the T and pi model. Whereas if I make it into 3 segments, now the delay is for the L model is actually 2 by 3 RC, which is actually reduced from RC to 2 by 3 of RC. Pi model, it remained the same RC by 2, and T model also remained the same RC by 2. Okay. And if I actually make 10 segments for the L model, pi model, and T model, and if I do the 10 segments, right, I will actually get RC by 2 here, almost close to RC by 2 for the L model. So it is actually decreasing. So if I had one segment of the wire with a characterized with a resistance of R and C, and if I use the L model, I'll get the delay as RC. If I make 3 models, I'll actually get a decreased delay of RC by 2 RC by 3. And then finally, if I make it 10 segments, I'll get close to RC by 2. For the pi model and T model, it was giving me RC by 2 in the one segment. It was giving RC by 2 in the 3 segments. And in the 10 segments also, it is giving me the value of RC by 2. Same here for the pi as well as the T model. All right. So what it implies is, so if I have an interconnect, either use the pi model, which is more standard, or the T model. So both of them are gives us the correct estimate of the delay. So the delay of the interconnect with the resistance of R, characterized with the resistance of R and the capacitance of C, actually gives us a delay close to RC by 2. Right. So this is a more appropriate or a well accepted model. All right. So here in this particular 10 segments, the calculation is done in a way that, each of the segments has R by 2, the distributed resistance and then the capacitance. All right. So moving ahead. So this is one such example I wanted to give. So I have a driver inverter, and the driver inverter is connected by a long wire to the to the load inverter. So what it means is I have an inverter here, or it could be one part of the a subsystem 1 design, subsystem module number 1, and from here onwards we can say that this could be the another subsystem design. All right. Between this subsystem 1 and subsystem 2, there is an electrical wiring, or there is a basically an interconnect that is connecting the subsystem 1 and subsystem 2. And if I want to see the delay from the input here to the output here, which is connected by a long interconnect, then what should be that particular delay or the performance, right? So in this particular lecture, we will just try to see what is the overall capacitance or the resistance associated with this particular interconnect, as well as the driver capacitance, and then as well as the load capacitance, right? The driver resistance, switching resistance, and then the capacitance, parasitic capacitance, and then the load input capacitance, as well as the switching resistance, right? Before that, let's try to evaluate what should be the overall resistance and then the capacitance of this long interconnect. So this particular long interconnect wire of 1 mm wire with a width of 0.125 micrometer and then the thickness of 0.22 micrometer. The capacitance is characterized as 0.2 femtofarads per micron of length, right? So if it is 1 mm wire, the overall capacitance of this particular wire will be nothing but 0.2 femtofarads, right, multiplied by, so 1 mm wire, so I'll have to have multiplied by 1000 in terms of micrometers. So this will be 0.2 femtofarads per micron of the length multiplied by 1000 microns. So I will actually get somewhere around 200 femtofarads, right? So this is what it is, 200 femtofarads is the overall capacitance of this long interconnect. So the interconnect is actually characterized with the dimensions given 1 mm width and thickness, and it is also characterized with the capacitance per unit length of the micron as 0.2 femtofarads per micron. The resistance of this particular wire is nothing but 800. That is what we had calculated in the previous slide. Again, just to reiterate, it will be rho L by T by area. Area is nothing but thickness multiplied by width. So it will be 2.2 micro ohm centimeter multiplied by 1 mm divided by 0.22 micrometer multiplied by 0.125 micrometer. So this is the width and then the thickness. This is the length. Gives us 800 ohms. So I now calculated the resistance of this wire and then the capacitance of this wire, which is 200 femtofarads, and the resistance is 800 ohms. Let's try to understand what should be the switching resistance and then the parasitic capacitance of this driver, and what should be the input capacitance of this particular loaded inverter. All right, so let's come back to this unit NMOS. So the unit NMOS transistor will give me a switching resistance of 10 kilo ohms. So assuming this is a long channel model, right? So the switching resistance we got was around 10 kilo ohms. The capacitance was on an approximate value we used to take 0.1 femtofarads. So if I have a unit inverter of 2:1 ratio, so the input capacitance it sees is a 3C capacitance, the parasitic is 3C. Here, I used to get a 3C value as 0.3 femtofarads because unit NMOS transistor's capacitance is 0.1 femtofarads. So the overall capacitance should be 3 into 0.1 femtofarads, so 0.3 femtofarads. The switching resistance for a size of 3, 2 is to 1, which is nothing but the size of the 3, will give me 10 kilo ohms. Right? So in that sense, if the driver is 30, 10 multiplied by 3, so 10 times the unit, 10 times the gate size of this particular driver inverter is 10 times more than that of the 2 is to 1 inverter. So in that sense, my resistance, the switching resistance, is likely to decrease by 10 times, and my capacitance, instead of 0.3, it was going to have multiplied by 10 times. And similarly, on the load side, if it is 2 times more than that of the gate size is 2 times more than that of the unit inverters, 2 is to 1 inverters size, then the switching resistance will get decreased by 2. The capacitance is going to increase by twice. Right? So the capacitance will be, instead of 0.3, it will be 0.6 for the load one, and this will be 0.3 multiplied by 10 for the driver one. Right? So for the driver, 10 multiplied by 3, so the switching resistance of the driver turns out to be 1 kilo ohms. The switching resistance of the load will be nothing but 5 kilo ohms. Capacitance will get multiplied by 10 times, so it will be, instead of 0.3 femtofarads, it will be now 3 femtofarads. And the load will be, instead of 0.3, it will be 0.6 femtofarads.